This is a continuation from the previous video where we discussed about differentiation. Today also, in this video as well, we will be discussing differentiation, but going a little bit further ahead, talking about the applications of the process of differentiation. Also a slight bit of revision from the last video where we will be discussing a little more about the chain rule that we discussed right at the end of the last video. My feeling is perhaps you need a little more awareness of this. So we'll take up a couple more examples on chain rule, and then we will move on and discuss some applications of differentiation. Now with chain rule, you can get some fairly interesting functions, like for example e raised to the power say tan x. Now in all of these problems which apparently involve your chain rule, where you have a function of another function, what we always do is first we look for a derivative of the first function. Now e to the power anything has derivative e to the power anything, and then you multiply by the derivative of that anything, and that's x square x. That's one simple example with the chain rule. Another example of this chain rule, for example, if you have something like root of sine x. Now how do you differentiate this? You will recall that if y equals root x, then dy by dx equals 1 by 2 root x. This is something you might recall from my previous video. Now here the first function is the root and the second function is sine. Now when we use the chain rule, the first thing we do is we find the derivative of the first function. Now for the first function, which is root, the derivative is 1 by 2 root. Inside the root you have the second function, and when you are finding the derivative of the first function, you leave the second function untouched, you do not disturb it, and then you multiply by the derivative of this second function. So then you multiply here with the derivative of this second function, which is now cos x. So that's chain rule. Now you can sometimes end up having more complex functions. For example, you might have something like sine of root of x squared plus 3x. Now you have a function sine, then you have a function with root, and then you have this function here. So here what you will be doing is you will be going stepwise. What you do is take the derivative of this first function first, and the derivative of this function is, in place of sine you end up with cos. The second and the third functions are left untouched. Then what you do is you multiply by the derivative of the second. Now the second function, when differentiated, gives you, it's a root, so you get something like 1 by 2 root, and then you multiply by the derivative of this function, which is 2x plus 3. So these are some examples on what we call the chain rule, and I'm sure with these examples you should be fairly clear now as to when and how to apply this chain rule. I've told you the quick method of doing it. Of course, whenever you're in confusion, you can always use the complete process of substituting this as z and then calculating the derivative of y with respect to z and then multiplying it with the derivative dz by dx, and that's legitimate as well. Till you have enough practice with this, you can try the longer process. The moment you start feeling confident with a bit of practice of this, you can start sticking to this process. So that's the brief revision of chain rule, and we now move on and discuss the geometrical meaning of derivative. And before we can do that, we'll have a brief discussion about slopes of straight lines and curves. So to start with, we discuss the slope of a straight line Now what is the slope of a straight line? It's the tangent, that is the tan of the angle which the straight line makes with the positive direction of x axis. Let's have a look at an example. Imagine that this is the y-axis and this is the x-axis. This is positive x, the opposite direction would be negative x, positive y, and the opposite direction would be negative y. Now, what is slope of a straight line? Let's draw a straight line, say this. Now this straight line makes an angle over here with the positive direction of the x-axis. Now that angle is this theta. Now tan of this theta is the slope m of this straight line. Now in this case, theta is measured anti-clockwise from the positive x direction, and therefore it's a positive angle. Generally in mathematics, when we measure angles, anti-clockwise angles are taken as positive and clockwise angles are taken as negative. This is a positive angle. Since the angle is positive, its tan is also positive, so this line has a positive slope. It is an upward climbing line. So for an upward climbing line, the slope is going to be positive. Now for measuring slope, we measure angles from the positive direction of x-axis, and the moment the angle exceeds 90 degree, the angle would then be measured as clockwise, as I will just illustrate in the next example. Let's take this one up. Positive x, positive y, and this time our straight line is like this. And this time you will notice that the line makes an angle theta again. Now it's a downward sloping line. The slope is downward, and now the angle will be measured clockwise. If you start with the positive x direction and move towards the line, you end up moving clockwise, and clockwise angles are negative, and so the slope would also be negative. So slope of course still remains m equals tan theta, and in this particular case here tan theta is negative because theta is negative. Over here theta was positive, so tan theta and therefore slope were also positive. Now very briefly I would like to introduce to you the concept of the equation of a straight line as well. Now for a straight line the equation goes somewhat like this. The y coordinate, y of any point on the line, equals mx, m being the slope, plus c. Now here this c is the y-intercept. Now what is y-intercept? Y-intercept is the y-coordinate of the point where the straight line intersects with the y-axis. In this case, as you can see, this is the y-intercept. In this example, this here is the y-intercept. So this is the equation of a straight line. I'm sure in your junior classes, class 9, 10, etc., you learned how to draw graphs of equations like this, and what you are getting acquainted with now is the equation in the form of slope and the intercept. So the moment you are aware of the slope, you're aware of the intercept, the y-intercept, you can easily sketch a straight line on a graph. Now that's slope for a straight line. Now slope of a curve. Now a straight line has a constant slope. The value of theta is same everywhere. So wherever you might measure theta, if you consider a positive x direction and take theta, you end up take the angle which the straight line makes with positive x direction. That angle does not change anywhere at all. So for example over here as well, if you consider the positive x-axis direction, then the angle theta which the straight line makes with the positive x direction doesn't change anywhere. So a straight line has a constant slope, but with curves that's not going to be the case. So how do we define the slope of a curve? Well, slope of a curve at a point is the slope of its tangent at that point. Slope of a curve at a point is the slope of its tangent at that point. Now let's take an example here and make it more clear to you. This says the y-axis, this is the x-axis, and here is our curve. Now we are interested in finding the slope of this curve at this point. How do we go about doing that? Well, we draw a tangent at this point to this curve, and this tangent has a certain slope. Now how do we measure the slope of the tangent? The tangent is a straight line. This is the angle theta. So the slope of this straight line will be tan of this theta, which in this case you can easily notice is positive. So at this point, the slope of the tangent or the slope of the tangent to the curve is tan theta, and that tan theta is also the slope of this curve at this point. So let's say the point is P, then the slope of the curve at point P is, the slope of the straight line, which is tan theta. Now you might easily notice that with a curve, the slope at different points will be different. So if I draw a tangent at this point, I have a different value of theta, let's say theta prime, and so at this point we have a completely different slope. And therefore, the important thing that you need to remember here is that for a curve, the slope is going to be different at every different point. So this is something from coordinate geometry that we'll be using in interpreting the meaning of derivative. Now we are going to interpret the geometrical meaning of a derivative. Now, what's geometrical meaning of derivative? Well, you're pretty much aware that for any relation between y and x, we can draw a graph. For absolutely any relation between y and x, a graph can be drawn. Now, with those graphs, we will be looking at the meaning of a derivative at a given point. For example, suppose you're given a function y equals fx. This here is the y-axis, this is the x-axis, and we've been given a function y equals fx. Okay, this is a function. What we'll do is we'll draw a graph of this function and try and see what a derivative at a given point would mean in the context of this graph. Now let's have a look at this point. Now this length here is clearly x. Then let's also draw this vertical line here from this point. This width here, this little length, is a small change in x, say dx, and this height here is y or fx, right? So over here we have y. Now have a careful look. This here is dx, and this from here to here, this length is x. Similarly, this length is y, or let's say this length is y. Then this further change in y would of course be dy, the change in y. So over here we have this dy, correct? Now we are going to try and have a look at the slope of this curve at this point. So to do that, what I do is I draw a tangent at this point. I've done that. This is the tangent. Now the slope of the curve at point P will be tan of this theta. Now if you observe carefully, you look at this little triangle here, if this is theta, then this angle here will also be theta. Now what is tan theta therefore? Tan theta now is equal to, if you look at this little triangle, it's dy by dx. So a very interesting observation. What's that? The slope of a curve at a point is equal to the derivative of the corresponding function at that point. So let me write the conclusion down here. Derivative of a function at a point is the slope of its graph at that point. Now this is a very interesting and very important conclusion that we have drawn, and will be used very, very frequently all throughout the physics that we are going to learn. The very first application, which comes more from mathematics than physics, is again very heavily or very frequently used in physics, and that's the use of this idea, this concept, in calculating the maximum or the minimum value of a function. But before we can do that, one little concept and you'll be good to go. Let's say we have a function y equals fx. Then the derivative of this function, dy by dx, we are representing as f prime x. Now even this is a function of some sort. We can always differentiate this function again, and then we would get what would be called a second order derivative or a second derivative, double derivative. Let's do that. Now the double derivative would be written as d square y by dx square. That's the notation. When you take a derivative of the derivative, it is represented by d square y by dx square. And over here in this notation we'll be describing it as f double prime x. So what's double derivative? Well, derivative of the derivative. For example, if we are given y equal to x cube, then the derivative will be multiply by the power and then reduce the power by 1, and that's the derivative. Double derivative will be the derivative of the derivative, and that's d square y by dx square, and it equals the derivative of this quantity here. Now 3 times the derivative of x square. What's the derivative of x square? Multiply by the power and then reduce the power by 1. And so you end up with 6 times x. So that's the meaning of double derivative. Now, what does double derivative tell you about the graph? Graph and double derivative. What's the meaning of this? Now see, double derivative is the derivative of the derivative. That is, it is the rate of change of derivative. Now graphically, derivative is slope. So double derivative is the rate of change of slope. And therefore, when your double derivative is positive, it indicates increasing slope. So suppose this is a graph here. These are the x and y coordinate axes, and this is the graph of some function. Now, in this particular case, what you will easily be able to notice is that the slope is increasing. If you draw a tangent here, it comes out like this. You draw a tangent here, it comes out like this. You will easily notice that the angle is increasing, and if the angle is increasing, so is the slope. So over here, slope is increasing, which essentially means that the double derivative or the rate of change of the derivative is a positive rate of change. So increasing slope means double derivative is positive. That is going to be the case when the slope increases. Now think of the opposite possibility. What if we have a case with decreasing slope? A typical graph with decreasing slope would be somewhat like this. Now what you notice is the slope is greater at first, and then the graph kind of becomes more and more horizontal, and that would indicate to us that the slope is decreasing. And in this scenario, when slope is decreasing for this graph, what it will mean in terms of the double derivative is that the double derivative will be negative. Now, why negative? Because a decreasing rate of change would be a negative rate of change, and an increasing rate of change would be a positive rate of change. So here we have a positive rate of change of the derivative. That means a positive rate of change of slope. Slope is increasing. Here we have a negative rate of change of derivative, and that means the slope is decreasing. Negative rate of change indicates decrease. So that's the graphical look at derivatives. We will now be looking at maxima and minima, or the maximum or minimum values of functions, and how we calculate those using derivatives. Maxima and minima. Consider a graph of a function. This is the x-axis, y-axis, and let me draw the graph. Let's say the graph of a function is there. It's like this. Now, you will observe that for this particular graph, here is the minimum value of the function, and here is a maximum value of the function in this range of values of x. So here in this range of values of x we have a minimum value of the function, and here in this range of values of x we have a maximum value of the function. So this point would be called minima, and this point here would be called a maxima. At the minima, if I draw a tangent, I get this. At the maxima, if I draw a tangent, I get this. Very easy to notice here now that at both maxima as well as minima, the tangents are parallel to the x-axis. At both minima as well as the maxima, the tangents are parallel to the x-axis. And wherever tangents are parallel to x-axis, it means they make zero angle with the x-axis. And therefore, at both the maxima as well as the minima, the slope of the curve is 0. So at maxima as well as minima, the slope of the curve or the graph is 0. At maxima as well as minima, the slope of the graph is going to be 0. And if the slope is 0, so is the derivative. So at maxima as well as minima, the derivative of the function is going to be 0. Of course, this graph is the graph of some function y equals fx. The derivative of this function at minima as well as maxima will be 0. But then, how do we distinguish between maxima and minima? Now have a look closely at the minima. At the minima, what will you notice about the slope here? Have a look at the graph. Now the slope here, as you can see, is increasing, right? At the minima, the slope of the graph is increasing, and therefore at minima the double derivative is positive. Easily noticeable that at minima the slope is increasing. At maxima, again it is easy to notice, as you get close to the maxima, the slope of the graph is decreasing and eventually it becomes 0, and then it even becomes negative. So at maxima the slope decreases, therefore the derivative of the derivative, that's the double derivative, is going to be negative. This is how we recognize maximas and minimas in simple functions. Let's take up a couple of examples to be able to identify maximas and minimas and to calculate them as well. So one simple example, first one we are taking up. Suppose you are given y equals x square plus 5x plus 10, and we are interested in finding out its maximum or minimum value, whatever we can find. Also we have to figure out whether it has a maximum value or a minimum value or both. So let's first do the first thing, and that's finding the derivative. dy by dx. Now what's the derivative of this thing? X square when differentiated gives us 2x. You multiply by the power, reduce the power by 1. No need to write 1. 5 times x to the power 1. X to the power 1, the derivative will be 1 into x to the power 0, which again becomes 1, and the derivative of 10 will be 0 because it's a constant. So what do we have here? 2x plus 5. We are aware that this derivative would be 0 at both maxima as well as minima. So let's say this derivative equals 0 at some point. Now at that point the function will either be maximum or it will be minimum. Now if we solve this equation, what do we get? We get x equals 5 by 2 plus 5 by 2. So that means when x equals 5 by 2, this function has either a minimum value or a maximum value. Now whether it's maximum or minimum can be determined only after differentiating one more time. Now this 2x plus 5 was dy by dx. So we differentiate again to calculate d square y by dx square. Now that will be a derivative of 2x plus 5. So 2 times the derivative of x to the power 1, we get a derivative that's equal to 1 as we just found out. So derivative of x will be 1 plus the derivative of this constant is 0, and so we get 2, which is positive. Now plus 2 being the derivative, what we've really discovered is that the function must have a minima, because the double derivative of this function is positive all the time. You don't even need to know what value of x. For all values of x, the double derivative of the function is positive, so it can only have a minima. So a minima exists, and in fact we know that only a minima exists. There is no possibility of a maxima here. So what's the minimum value of y? Well, y is minimum. We already know y is minimum or maximum when x was 5 by 2. And by finding the double derivative, we found out that it is minimum. So, the minimum value of y will be calculated by substituting x as 5 by 2 in this function here. So in place of x, we substitute 5 by 2. Let's see what we get. 5 by 2 whole square plus 5 into 5 by 2 plus 10. And that's 25 by 4 plus 25 by 2 plus 10. You can multiply by 4 throughout, and you have 4 here. 25 plus 50 plus 40, and that's 115 by 4, and that's the minimum value of y here. So we've learned how to calculate minima in this particular case. We can also take an example of a function where we get maxima. Let's take an example, and this time we'll be calculating the maxima of, I've given it away actually, I've already told you there's going to be a maxima, minus x square plus 10x. That's the function we are given. Let's quickly calculate the derivative. Dy by dx minus 2x plus 10. For minima, the derivative must be equated with 0, and so we get x equal to 5. Now we have either a maxima or a minima at x equal to 5, and to figure out whether we have a maxima or minima, we do a double derivative. We do double differentiation. We take a derivative of the derivative. Now 10 is a constant, the derivative is 0, and for minus 2x the derivative is minus 2. See, the constant remains as it is, and then you multiply with the derivative of this function. X to the power 1, as we figured out here, has a derivative 1. So the double derivative is minus 2 now. Now minus 2 would mean you can only have a maxima. And now the maximum value of y can be calculated by substituting x equal to 5 in this function. So the maximum value of y is minus 5 square plus 10 into 5, and that's 50 minus 25, so you get 25. And that 25 now is the maximum value of y in this particular relation. So here what we've done is we've learned how to calculate the maximum value of a function, we've learned how to calculate the minimum value of a function using the method of differentiation. This is an extremely powerful technique that we will be using very, very frequently in physics, starting from this the first chapter of mechanics, and that's kinematics, and all the way through the entire physics curriculum of grade 11 and grade 12, and perhaps even till practically as long as you learn physics, you will continue to use this technique.